science classroom. So this week we're going to keep learning and keep diving in deeper into what we've been talking about, which is static charges. Remember, we were trying to answer the question of why do things stick together when they come out of the dryer? And that led us to learn and discover about static charges. So let's dig a little bit deeper. How and why are these things becoming charged? What is happening with these materials? So why do some things like to become negatively charged, kind of like the balloon when we rub it with the sweater? And why do some things like to be positively charged, like the sweater, again, when we rubbed it with the balloon? So what's really happening there? So we're going to dig a little bit deeper now in this unit and look at what are all materials made of? So like, what are these made of? That is going to be our focus. So let's start with a little thought experiment. We have a piece of paper, and what would happen if we cut it in half? Let's say we take piece of paper, and we cut it in half, and then we cut that in half, and then we cut that in half, and we cut that in half, and then we cut that in half, and we cut that in half, we cut this in half, and we keep cutting it in half. And as we keep cutting it in half, will there ever be a point where it's no longer paper? Or will it always be paper? So what do we think? If we cut paper in half over and over and over again as we get to smaller and smaller pieces, will there ever be a point at which it is no longer paper? Or will it always be paper? What do we think? So these are the thoughts of other students that have about cutting the paper in half over and over and over again. So, for example, student A, they think that no matter how you cut the paper, it will always still be paper. No matter how small it gets, the stuff that is so small that it's still going to be paper. Or we have student B thinks that if we keep cutting the paper, you'll eventually get stuff like wood. So since paper is made out of wood, or like wood mulch, if you keep cutting that paper more and more, then eventually you're going to get what it started with, which is wood. Student C thinks that if you keep cutting that paper over and over and over again, you're just going to get dust. And last, student D thinks that if you have fancy enough equipment, then you can continue dividing the paper into smaller pieces. But eventually, it would not be paper anymore. You would have tiny pieces that are different from paper. So you're going to cut it so small that the pieces are going to be different with what we started with. So what do you think? Which student do you agree with the most? So these questions and answers that we've been trying to unravel over the years have been the same questions we've been pondering out for thousands and thousands of years, way back to ancient Greece. So over 2,000 years ago, around 300 BC, we had these very famous philosophers. We had Aristotle, which is well known, and another which you may or may not know, who is named Democritus. Well, these ancient philosophers were our first scientists, and they were scientists because they were thinking and pondering about the world. They were wondering and sought to explain what it is and how everything works. So they were wondering about the same questions of what are all these things made of. So our first model that we'll talk about came from Aristotle. We'll call his the continuous model because he thought matter was continuous. And so that means that any materials such as paper, gold, rock, what have you, it can be divided into smaller and smaller pieces forever. You can always continuously divide it. It'll just keep getting smaller and smaller and smaller and smaller forever. But each piece, no matter how tiny, will always look and behave like the larger pieces. They have the same properties. While the other ancient Greek philosopher, Democritus, he had a different idea. We'll call his model the particle model. And he believed that matter is made up of these tiny pieces, these tiny particles that are way too small to be seen with the human eye. And they can't be broken down into smaller pieces. So he thought that if you cut like rock or paper into smaller and smaller pieces, eventually you're going to get to the smallest piece and it won't be able to be divided anymore. And these pieces or these particles group or stick together in different combinations to make up all materials. And he also thought too that these small pieces will act differently than what they made up. So if we cut paper continuously until we get to its smallest piece, that smallest particle is different than paper itself. So those are our two models. We have continuous, where we think that matter can be divided continuously forever and the smallest parts act the exact same as the bigger parts. Or we have the particle model, where if we eventually cut something so small, we're going to get a piece that we can no longer cut anymore, and it's going to be different than the whole that it made up. So which do you agree with, the continuous or the particle model? What do you think? So as we think about that, we're going to do an at-home experiment. You can do this at home if you like. You can do this with me, or you can just watch what I do, or you can do it later. So I'm going to set up the experiment up here on this table, and then we'll do it together. All right. All right, I am all set up for our at-home experiment. So what we're going to be doing as we think deeper into what materials are made of, we're going to be using a little bit of math. Don't worry, it's not hard math. As long as you know what 5 plus 5 is, which is 10, we're in good hands. So we're going to be looking at volume. And remember, if you remember from previous science classes, volume is basically the amount of space an object takes up. It's its entire amount. So it's like measuring the three-dimensional size of an object. So for example, we have a textbook and we have a workbook. So they are both have about the same length. They both have about the same height, but they have different widths. So it means that they have different volumes because they both take up different amounts of space. This one has a bigger volume, while this one has a smaller volume than the textbook. We'll also be looking at, when we're measuring volumes of fluids, you have to be careful when you measure it because there's something called a meniscus. So when we're measuring our fluids, you have to make sure that you measure the bottom of the meniscus. And I will get to that in a second because we're measuring our fluids in something called a graduated cylinder. So you'll need a graduated cylinder, but I'm sure you don't have one at home. So you can use any kind of measuring cup to use that's used to measure fluids, like these. This would be a good measuring cup, or this one could be a good measuring cup. Anything that measures the volume of fluid. But I'm going to be using these graduated cylinders because I'm only going to be measuring small amounts of liquid. And when we measure small amounts of liquid, or when we measure any amount of liquid in science, we measure it in liters. And like I said, we're measuring small amounts, so that would be in milliliters. So for example, if you know, you can get a liter of soda, or in my case, a liter of coffee. And when we're measuring small amounts, we measure it in milliliters. So essentially 1,000 milliliter will be 1 liter of soda or coffee. For this experiment, you'll also need some water or some ethanol. But you probably don't have any ethanol lying around the house. So we're going to be using acetone, which is just a fancy word for nail polish removal. So that's what we'll be using. I will also be using, but it's not necessary for you to use if you want to do this at home, are just droppers. This just helps it become a little bit more scientific and make sure that I'm very specific about my measurements. And we'll also be recording everything on a data table. So when we measure fluids in a graduated cylinder, like I said, there's going to be something called a meniscus. So let me show you what that looks like. So let me bring this up. So the meniscus is that bubble. You see the bubble on the 5? So what happens is that there's something called surface tension that causes the bubble of the fluids when you're measuring it. And you want to measure the bottom of that bubble, and that's the meniscus. So fluids typically have this kind of curvature or concave or convex curvature, and you always measure the center bottom. So for water and ethanol or acetone, it's going to be concave, so you see how it dips down, and you measure the bottom of the meniscus, the bottom of the bubble. All right, so what we're going to do is we're going to measure water and water, acetone and acetone, water and acetone together. So we're going to take 5 milliliters of water, which I already have here in 1 volume. in one graduated cylinder. So that's 5 milliliters. Then we'll take another measurement that I will have to do next of 5 milliliters of water and another volume. So that will be 5. Then we're going to calculate it, which means that we just add them together. This is our prediction. So if we add 5 and 5 together, we should get 10 milliliters of our volume. So now let's do the experiment and see what happens. So I have already measured 5 milliliters of water in volume 1. So let's do it in volume 2. So I want to be precise, so I'm using my pipette and I'm filling it up to 5. And remember that the meniscus, or the bottom of the bubble, needs to be at that line. So I gotta look very carefully right about there. So I have 5 and 5. Now let's see if we add these two fluids together. Let's see if we get 10. So I just pour one into the other. And I shake it down a little bit to get every last drop. And look at that. We've got it right at 10. So we have 10 milliliters. So let's look back at our data table. So this is our calculated, this is what we predicted, and that is what we observed. So I'll write 10 milliliters. Will the same be true for our acetone? So let's pour this out and put in acetone. So I already have one of them set up. So as you can see, I have 5 milliliters of, see, it's not as flat, so you can't really see the bubble, but the bubble is right on 5. So the meniscus is right on 5. Now I have to have 5 milliliters of acetone here. So let me start filling that up with my pipette. There. So now we have 5 and 5. So I've got 5 milliliters of acetone for volume 1 and 5 milliliters of acetone in volume 2. Let's see what happens when I add them together. Will we get 10? So I'll pour one into the other carefully. Give it a nice tap, tap, tap that's gentle so I can get all of the fluid as I can in there. And let's see. Yep, look at that. 10 milliliters of acetone. So we look back here. We had 5 milliliters in volume 1. We had 5 milliliters in volume 2. We calculate or add them. We think that we should get 10 milliliters. And we observed, we have our evidence that we did indeed get 10 milliliters of acetone. So let's see what happens if we add water and acetone together. So let's say we have 5 milliliters of water. So let's call this one water. We have 5 milliliters of acetone, the nail polish remover. And we predict that if we add these two fluids together, we should get 10 milliliters of both. Now let's see if that happens. So instead of pouring this out, I already have some acetone in here. So I'm just going to take out some so that I get 5. Here we go. So there is 5 milliliters of acetone. Now let's do the same with water. So I've got, this one is our acetone. So we have 5 milliliters of acetone. We have 5 milliliters of water. Let's add them together and see what happens. So I take one and I'll pour it in. And I'll give it a little shake. Let's see what we got. Is that exactly 10? No. We lost some. It's not exactly 10. We are at, 9.6. Let me add that to our data table. So 9.6 milliliters. What happened? We're going to leave it on that note. How or why do you think this happened? What is happening on the molecular level? What is happening at the very smallest level? Can the continuous model explain this, where we continually cut pieces together and it's always going to be the same? Or can the particle model explain this, where if you keep cutting something in half over and over again, essentially you're going to get small pieces or small particles that are different than the total? Or do you think it's something else, something we haven't even discussed or thought about yet? So let's dive on in, learning in this class, and try to figure it out. And until then, I will see you next time. Bye, everybody.